Hey, welcome to Chapter 7, where we're going to be discussing chemical bonding and molecular geometry then at the end of this. So we're going to go over just kind of the basics of the two different types of chemical bonding really quickly. First, we're going to start here with ionic bonding. And ionic bonding is when one or more of our electrons are completely transferred. Okay, we've kind of talked about this in the past there. Where we're going to take one of our elements is going to form a cation because of this, and the other is going to form an anion because of this. And here, as my example, I've got my sodium and I've got a chlorine there. And notice that I've got my sodium there. It's written as it's got like that one electron out there. Okay, what that really is doing though is I'm saying that I've got sodium has, from our previous chapters, has an electron configuration of 1s2, 2s2, 2p6, 3s1. And so this is really showing that 3s1 electron there. And then chlorine has the electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. Okay, and so what this is really showing is these are what we call the valence electrons. They're the electrons on the highest principal quantum number there, so that's why we're seeing 7 of them. We're seeing the 2 from the 3s and the 5 from the 3p there. All right. And so what we find with ionic bonds is that the reason that they occur is because everybody really kind of wants to look like a noble gas, and it really wants to have 8 valence electrons. Okay, so what happens here is if our sodium gives up an electron and becomes the sodium cation there, then its electron configuration becomes 1s2, 2s2, 2p6. Okay, and if we look at that, there are 8 electrons in the highest principal quantum number there. Okay, well then that one electron was given to the chlorine. Oops, sorry, that's sodium. And then that becomes a chloride anion. And its electron configuration goes 1s2, 2s2, 2p6, 3s2, 3p6. And if we look at that, then our chloride is going to have a valence of 8 electrons as well. And that makes them really happy. And that's why these bonds occur. That's why there is this transfer of electrons in ionic bonds, is because it makes each one of the elements more stable that way. All right, now ionic bonds are relatively strong, and the strengths of our ionic bonds come from a couple of different factors. All right, number one is it comes from, oops, pen. All right, it comes from the bond lengths, and it also comes from these charges that are placed there. Right, and we're not necessarily going to be doing any math on these, okay? But right, what I want to kind of point out is that the strength, which I'm going to give the symbol of E here, is equal to, all right, there's some sort of a constant in here, all right? And in chemistry, we give things constants. I'm going to give this the constant of a K. Sorry. And then there are 2 charges. Okay, and so if I've got a sodium cation and a chloride anion, right, those charges are 1 and 1. Okay, we're going to do like the absolute values of those. And then we're going to divide that by the distance between the sodium and the chloride. And that is the distance from, say, the nuclei of one of them, all right, and the nuclei of the other of them. Okay, so what that's putting out here is that the strength of these bonds is directly related to the charges. So if you have things that have larger charges, right, which we're showing as Q, they're stronger bonds. Okay, and if we've got larger ions, they're weaker. Okay, because it is inversely related to that. So smaller ions are stronger ionic bonds, right? Because in essence, like we've got these charged things that are stuck together. And so the bigger that charge difference is, right, it's kind of like magnets, right? They're stuck together with those opposite charges. The bigger the difference in that, the harder it is to pull them apart, so that bond is a little bit stronger. And the closer they are together, the harder it is to kind of cleave them. All right, next up, we're going to just kind of turn our attention then. That's basically what we're going to get out of our bonding. We're not going to really dive into the types of bonds too much. I just wanted to get out there, like, you know, the strengths of the bonds, and then also, you know, that they want to have these octets. All right, next up, we're going to talk about covalent bonds. And remember, covalent bonds is when we have nonmetals bonded together. All right, and so covalent bonds are a little bit different, right? Covalent bonds is where we have a sharing of electrons. Okay, and they're still trying to get octets by sharing electrons. And so this, though, comes into the fact that when they share electrons, there are a couple of different factors that are in play. Number one is that we have some attractive and repulsive forces here, and I'm showing that in my figure out here to the right. So if we think about how our atoms are made up, right, we've got these nuclei where we've got these positively charged things, right? And in those nuclei, right, we've got those positively charged things, and the nuclei themselves are going to repel each other, right? Because as we bring them together, these nuclei are going to repel each other because positive and positive things are going to repel each other. Right, and around each nuclei, as shown in kind of those like green-gray bubbles there, that is the rest of our atom, and that is where the electrons are. And remember that our electrons are negatively charged. And so we've got these negatively charged things out there, and so as we bring them together, we've got these negatively charged electron clouds, and they are going to repel each other because negative and negative things repel each other. All right, but right, the electrons from one of them, right, which is kind of shown, like if I got electrons out here, is going to be attracted to the positively charged protons of the other one that's out there, and vice versa. Right? And it just so happens that the attractive forces are slightly better than the repulsive forces in these, and that's why we get covalent bonds to take place. All right, now when it comes to the strengths of our covalent bonds, right, if we remember back to the end of our enthalpy chapter, right, we had that bond association energy. That is basically what these are here in a table form. But I want to just kind of point out a few things. And so I've got some in some blue boxes there, and I've got some in kind of like an orangey red box as well. Number one in the blue boxes, right, I just want to point out that, right, single bonds are weaker than double, which are weaker still than triple bonds. And we can see that as the average bond association energies keep increasing. Right, we got 350 for a single bond for a carbon-carbon double bond at 728, and our carbon-carbon triple bond it's 965, right? So it takes more energy to break them, right? So as we increase the number of bonds, we're also increasing the strengths of the bonds. In the red boxes there, right, notice that those are hydrogens bonded to halogens, and what this is really showing is atomic sizes. So if we think back to our periodic table, right, as we go down the periodic table, right, remember that atomic radii increases. Okay, so if we look at a periodic table, right, fluorine is above chlorine, which is above bromine, which is above iodine. And so as we increase atomic radii, sorry, the bond strength decreases. Okay, so again, right, we're just kind of touching base on our different types of bonds in there. All right, next off, let's look at, all right, we're going to start actually like building molecules. All right, and that's the biggest part of this chapter overall, is being able to draw Lewis dot structures and being able to actually draw different molecules as we kind of go forward. Okay, so we are going to do this by drawing what we call Lewis dot structures. All right, and to draw Lewis dot structures, the way that we do this is that we are going to draw the symbol, and then we're going to add one dot to each side around them. And we're going to assume that there's like 4 sides around anything that we're going to draw. Okay, so like I'm going to go across our second row, and so we're going to start with like lithium, right? And lithium has 1 electron. And so I'm going to show the Lewis dot symbol as being lithium, and it's got 1 dot around it. All right, next up I'm going to go to beryllium, which is the next one over there. Beryllium has 2 electrons. And notice that I am not pairing the electrons up. I'm adding them to one side before I start to pair them up. All right, next off, right, I'm going to go to our boron. Boron has 3 electrons, so 1, 2, and 3. Right, and I bet we can figure out where this is headed. All right, next off is carbon. 1, 2, 3, 4. And then nitrogen, 1, 2, 3, 4. Oh, now we've got 5. I can finally pair up over there. Because I'm really kind of doing it this way because electrons are negatively charged, and so they repel each other, so they don't want to pair up until they have to. That's why I'm kind of showing it this way, and that's the way we do it. Oxygen. All right, 1, 2, 3, 4, 5, 6. All right, now I put the electrons that are paired up on opposite sides just because, again, we want the electrons to kind of be as far apart as possible, but really you could put them next to each other and it's totally fine. All right, fluorine, 1, 2, 3, 4, 5, 6, 7. So 3 sides have paired electrons and 1 has a lone one. And then finally, going across, we have neon, which has all 8. And so there are 2 electrons on all sides of it. All right, so that's where we start with drawing our Lewis dot structures. All right, now this is going to help us to describe single, double, and triple bonds going forward. So single bonds in general like to share a pair of electrons. Right, my example here is showing some hydrogen atoms. All right, and so if we look at that, right, each hydrogen has an electron configuration of 1s1. Okay, so as they come together, right, there is those 2 red dots there, those are showing our electrons. When they come together, they can share those electrons. All right, and so that makes it feel like, right, each hydrogen feels like it kind of has 2 electrons around it. Sure, they're being shared, okay, but it feels like there's 2 electrons that are around each one of those hydrogens. And if we look at hydrogen, if we look at the periodic table, right, if we go right on the periodic table, the next element out there is helium. Helium is a noble gas, and it has an electron configuration of 1s2. Hydrogen is striving to look like a noble gas. Everybody wants to look like a noble gas. And so it feels kind of like it's a noble gas because it feels like there's two electrons. Sure, it's sharing them, but at least they're around there sometimes where it's got those two electrons. All right, same sort of an idea. If we were to bring a couple of fluorines together, all right, fluorine, remember, has 7 electrons, 7 valence electrons around it. So if we think about fluorine, it is 1s2, 2s2, 2p5, right? So it has 7 valence electrons. There's 7 of them in the highest principal quantum number. All right, now it is very easy to figure out how many electrons there are in the highest principal quantum number, or sorry, how many valence electrons there are in that highest principal quantum number. And for our main group elements, right, we can just count across our periodic table. Group 1 has 1 valence electron. All right, this is going to come in handy later. Group 2, 2 valence electrons. All right, we're going to jump all the way across to group 13. Sorry. Group 13 has 3 valence electrons. Group 14 has 4 valence electrons. Group 15, I bet you can guess, has 5 valence electrons. Group 16, 6 valence electrons. 17, 7, and group 18 is 8. Okay, so fluorine is in group 17. It has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7 valence electrons there. All right, if we bring fluorines together, right, if we bring them together, I'm going to draw those two as different colors just so you see. All right, each one of them had that one electron that's in there kind of in the middle. They're going to share those electrons. Okay, so each fluorine now kind of feels like it has 8 electrons around it. And fluorine wants to feel like a noble gas. Well, if we look to the right of fluorine on the periodic table, we have neon. Right? And neon has 8 valence electrons. Fluorine really wants to have 8 electrons. Well, the way that it does that is it can kind of share those electrons that are out there. All right. Now, when it comes to double bonds and triple bonds, okay, this is where we're going to share more than just one pair of electrons. So if we look at our oxygens down there, right, and I'm going to erase over here if I can. It's very slow. Right, our oxygens there, right, notice that they are sharing multiple electrons to get double bonds. So a double bond is actually sharing of 4 electrons. A single bond is sharing of 2. Okay, so an oxygen, right, has that 1, 2, 3, 4, 5, 6 valence electrons, right, because it's in group 16. And if I bring in another one, okay, so we're going to share those 2 electrons right now. If it was left like this, right, then each oxygen, I'm just drawing a box around one of them, but each oxygen, notice, kind of feels like there are 7 electrons around it, right? You can count those dots. But notice that if we bring in, right, those other ones, there, and we share another pair of electrons. So I'm going to bring in a couple more of them there. Okay, now, right, each oxygen, again, I could draw a box around the other side too. But now, right, there's 8 electrons there. And so oxygen, right, feels like there's 8 electrons. Right, which is kind of like that noble gas neon. That's what they're striving for. So that's why it's a double bond. If we notice our nitrogen there, nitrogen likes to form that triple bond because right, if it forms only a single bond, then it would have, right, 1, 2, 3, 4, 5, 6 electrons around it. But if we bring in 2 pairs of electrons, right, it has, each line counts as 2 electrons. So that triple bond, like the bonds, there's 3 bonds, that's 6 electrons. And then we've got the 2 other electrons that are out there, so it feels like there's 8 electrons around it by bringing in those extra ones. All right, so now let's start drawing some molecular compounds. Okay, so first off, in order to do this, we have to be able to add up the valence electrons. Okay, so remember, right, we are going to then use the group numbers in order to do that, right? Group 1 has 1 valence electron. Right, group 14 has 4 valence electrons, and so on. If you have an ion and it has a negative charge, you have to add an electron to it. If you have an ion with a positive charge, you subtract an electron from it. All right, then we're going to try to we're going to put the very first element that's written there. All right, it says the central atom is written first. Sometimes, for our purposes, pretty much always, unless you see a hydrogen written first. Hydrogens are always what we call terminal or on the outside. Okay, and so anything else that's written first, we're going to put it in the middle. Then we're going to draw single bonds in, and we're going to use up electrons. All right, and then we're going to start adding in pairs of electrons from the outside in to make octets. Now, sometimes we don't make octets, like hydrogen likes a duet. That means it only really wants to have 2 electrons around it. Boron and aluminum like to have sextets. That means 6 electrons around them, but pretty much everybody wants to have 8 electrons around them if at all possible. All right, now we're going to get some practice at these, and hopefully you do a bunch of them, right? Because the more of them that you work, just like anything else in chemistry, the easier they become. All right. Then if you have any more electrons, we're going to place them on the central atom at the very end. Then we're going to double check, does that central atom end up with an octet as well? If it doesn't, then we're going to bring electrons in to make some double bonds or triple bonds in order for us to get there. All right, the central atom is the only thing, right, in our case that can have an expanded octet. That means that it can have more than 8 electrons. And in order for it to have an expanded octet, it has to be in period 3 or below. All right, and so if you look at your periodic table, right, you've got period 1, is where hydrogen starts. Period 2 is where lithium starts. So sodium period 3 and below, and they have to be p block elements. Okay, and p block elements then are the ones that are way over here, right? So things out here, there's like aluminum, silicon, phosphorus, sulfur, chlorine, like things out there. They've got to be out there in order for us to be p block elements. So what that means is that they can't be things like lithium or sodium. Those are s block elements. So they have to be basically groups 13 through 18 in order for those to occur. Okay, so let's then draw the Lewis structures of SO3, ICl5, and NH4+. Okay, so number one, right, is we'll do SO3. So we're going to count the valence electrons. Okay, so sulfur. If you find sulfur on the periodic table, it's in group 16. So it has 6 valence electrons. Okay, oxygen is in group 17. Or sorry, is also in group 16. Sorry. It has 6 valence electrons. And there are 3 of them. Okay, so we have 6 valence electrons plus 18. So we've got 24 valence electrons to play with. All right, now what we do is we're going to put that sulfur in the middle. All right, we're going to put it in the middle, and then we're going to surround it by other things, the oxygens in this case. All right, because sulfur was the first one listed, and it's not a hydrogen, we're going to put it in the center. All right, now we're going to draw single bonds to the elements on the outside. And every single bond counts as 2 electrons. So we've put in 3 lines, so that's 6 electrons. So I'm going to subtract off 6. 24 minus 6, we're down to 18. All right, that was step 2, by the way, was draw single bonds. Okay, next off, right, is we're going to place pairs of electrons, number 3, on the outer atoms to make octets. Right, basically, we want to get to 8 electrons around each one of them. So oxygen, like look at that top oxygen right now, it has a bond. That's 2 electrons that it feels like it already has, so we can only put in 6 more. So 1, 2, 3, 4, 5, 6. Now that oxygen feels like it has an octet. So basically, we're going to be putting in 6 dots around everybody. So there's 6, 7, 8, 9, 10, 11, 12 when I fill up that next oxygen there. 13, 14, 15, 16, 17, 18. Okay, I put in 18 electrons. I don't have any more electrons to put in. Step number 4. Place any other remaining in the central atom. I don't have any more to put in, so I can't do that. All right. Number 5. If our central atom does not have an octet, we're going to form multiple bonds. Okay, so step 5 here is, right now our sulfur has 3 bonds to it. So it only has 6 electrons. So I'm going to bring in a pair of electrons here. Okay, and what that does is that gives our sulfur an octet, because now there's 4 bonds to that sulfur, right? And so that's 2, 4, 6, 8 electrons, so it now feels like it has an octet. That top oxygen has 2 bonds, which is 4 electrons from that 2 bonds, and it has 4 dots. It also still feels like it has an octet, so I didn't mess up the oxygen by doing that. Now you might be smart, be thinking to yourself, why did I choose that oxygen? I could have chosen any of the oxygens, and that is something that we'll get to in a little bit. That is going to be called resonance, that I could have chosen any of them, but I just chose that top one, and that's perfectly fine. We'll talk about why you could choose any of them in a little bit. All right, next up is ICl5. Okay, so we're going to go through, so I, right, we're going to count up our valence electrons. I is in group 17. Has 7 valence electrons. Chlorine is in group 17. 7 valence electrons, but there are 5 of them. Right, so that's 35 valence electrons. So we have 42 electrons that we can play with here. All right, now we're going to put our I first. We're going to surround it with our chlorines, and we're going to put in single bonds. So I'm putting in 5 single bonds, which is 10 electrons. We're down to 32 that we can play with. Now we're going to put in our dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, I have put in 30 electrons. All right, I've run out of electrons to put on the outside. Okay, now it says, wait, we're going to, number 4, place any other electrons on the central atom. I'm going to place them there on that iodine. Okay, now the iodine has way more than an octet. If you look at it as 5 lines, that's 10 electrons, plus it has 2 more, it has 12 total electrons. But iodine, again, right, is a p group element, and it is well below period 3 on our periodic table, right? And so it's okay to have what we call an expanded octet. It's okay to have more than 8 electrons. So that is, we're done with that one actually, right? Because we don't have to bring any more in to try to make that octet. All right, last one. Let's do NH4+. All right, so nitrogen, right? Nitrogen is in group 5, so it has 5 valence electrons. Hydrogen is in group 1, so each one of them has 1 valence electron, right? And so there are 4 total, 4 times 1. But then we have a +1 charge. Okay, remember a +1 charge, right? When we've got a +1 charge, we have to subtract an electron. So 5 + 4 - 1 is 8. All right, we got nitrogen. We're going to surround it by hydrogens. We're going to put in our single bonds. There's 4 lines, that's 8. We've actually used up all of our electrons. Okay, but now let's think about it. Hydrogens are cool having only 2. And each one of them has 1 bond that counts as 2, so each hydrogen's happy. Our nitrogen, let's look at it. It has 4 bonds. Each bond counts as 2, so it actually has 8 electrons around it. It's happy. It's got its octet. Everybody's happy. The only thing we have to do on this is, because there's a charge, we put these pictures in brackets like this and put the charge on the outside to tell whoever's looking at it that this is actually an ionic species. All right. So next up, we're going to talk about that formal charge and resonance structures. Okay, so a resonance structure is where we can have various forms of the exact same molecule. All right, and resonance structures technically are where electrons are being transferred from one region to another. They actually are moving around. They are free to move around the entire molecule. Electrons aren't really trapped where we draw them to be. They actually can move around the entire molecule. All right, and so we can also determine formal charges. And formal charges are going to help us determine what is the best figure that we come across. All right, so let's look first at our SO3 that we drew before. Right, and remember that I drew it like this. All right, well, I drew it with that double bond to that top oxygen. Okay, well, I could have actually drawn it, and we draw this as like a double-sided arrow like this whenever we're forming resonance structures. I could have actually drawn this where I actually had the double bond to this oxygen instead, right, that one there. Or I could have drawn it where the double bond was to this oxygen. These are all valid ways of drawing this. All of them have the oxygens having octets, and all of them show that sulfur with an octet. They're all valid ways of drawing this exact same molecule. Right? And in the real world, what's happening here is that the electrons are actually traveling around, and the double bond is between the sulfur and that top oxygen some of the time. Some of the time it's between the sulfur and that bottom right oxygen, and some of the time they've moved over there where the double bond is between the sulfur and that bottom left oxygen. The electrons are moving around and being there sometimes. So all of these are valid ways of drawing them. When we've got different valid ways of drawing a molecule, what we can do is we can determine what we call a formal charge. Right? And when we determine a formal charge, this will help us determine which is the most stable form of our molecule. And in order to determine a formal charge, we have to be able to count up a few things. All right, so to determine a formal charge, we can do the number of valence electrons if the atom were a neutral free atom by itself. So meaning like if it was an oxygen, oxygen is in group 6, the number of valence electrons would be 6. Sulfur is in group 6, the number of valence electrons would be 6. All right, the number of sticks, right? So we'd subtract off, it's very hard to see that, it's a minus, and that's a minus. So minus the number of sticks and minus the number of dots. So if I wanted to do the formal charge of this bottom left oxygen there, okay, number of valence electrons is 6. All right, next off, we're going to subtract off the number of sticks. Okay, I'm only looking around the oxygen itself, not in the entire molecule. So around the oxygen, there's only one stick, one bond. And then how many dots there are. Around that oxygen, there are 6 dots. So 6 minus 1 minus 6, it has a formal charge of -1. Right now, if we were to do the same thing for, say, like the top oxygen, okay, well, oxygen, it has 6 valence electrons. The number of sticks around that one is 2, because there's a double bond. Minus the number of dots, there are 4 dots around that. It has a formal charge of 0. All right, now overall, our molecules are most stable. We can sum up all of these things and find all of them and everything. So let's do the sulfur in that one. Sulfur has 6 valence electrons. The number of sticks around our sulfur is 4, and there are 0 dots. So sulfur is +2. And then the bottom right oxygen is the exact same as the bottom left oxygen because it has 1 stick and 6 dots around it, so it's also -1. Notice that the sum of the formal charges is equal to the overall charge of the molecule or ion. Okay, so this is a molecule. There's no charge in this. We have 0, -1, -1, and a +2. If I'm taking all of those things together, right, there's a 0, there's a -1 from each one of those oxygens, and there was a +2. Right, all of those together add up to being 0. If it was a ion, they should all sum up to being whatever the ion charge is. All right, and then molecules are most stable when the charges have the smallest values possible. So we're going to use that to be able to look up which one's the best overall shape at some point. All right, lastly, we're going to look at molecular structures and polarity. I'm going to tell you that what you really are going to want to do whenever you're doing molecular structures is a lot of the time is there's a nice little table. We can use it as a little cheat sheet. All right, we're going to run through them really quickly. But again, drawing them and then looking at the table, which is a few slides away, is going to get you a really long way as you're going to be able to have all the resources that you need. Because again, I don't think that it's ever useful for you to memorize a bunch of stuff. Oops, I jumped through stuff. We'll do all of those shapes anyway, so it's not a big deal that we jump through that slide. All right, so number one, though, I do want us to get, like, when we've got geometry and shapes, all right, geometry and shapes are a little bit different from each other. Geometry is how our electrons are around our central atom, and the shapes is what it looks like. Okay, so like our top one there is methane. All right, and methane is given what we call the shape of a tetrahedral shape because it looks like a little tetrahedron there. So that's a tetrahedral shape. Okay, and it has what we call 4 regions of electron density, which we're going to call RADs. And notice that all of them are bonds. Okay, now if I move down to ammonia, it also has 4 regions of electron density. 3 of them are bonds, right? I'm going to draw those as those little red lines there. And then it has this one lone pair of electrons when it was drawn out. Okay, so both of these have the same electron geometry. Okay, but their shapes are actually different from each other. Okay, the shape of this one down here isn't tetrahedral. The shape of ammonia is what we call trigonal pyramidal. All right, so what that means is that it has formed a triangle. The base is a triangle, and then we've got this little pyramid above it. That's where the name comes from, trigonal pyramidal. But it's slightly different than a tetrahedral, as that it's not quite as elongated there. All right, the very bottom one, our water molecule, also has 4 regions of electron density. But notice that it only has 2 bonds. The oxygen is bonded once to each hydrogen there. There's 2 bonds there. And then there are 2 lone pairs. we don't see the lone pairs when we look at the actual shape of the molecule, and that's why the shape is different from the electron geometry. So the electron geometry for this is still the exact same as the other ones, but the shape of this one is something that we call bent. Because when we look at the molecule itself, it just kind of looks like this little like bent V. All right, now there are all different types of shapes and all different types of, for different types of electron geometries. All right, so there is like a linear geometry, linear electron geometry, where we've got two regions of electron density and no lone pairs. It's going to be linear, right? It looks like a line. Okay, we can have three regions of electron density. If all three of them are bonds and there are no lone pairs, then, okay, we call this trigonal planar. It makes a triangle, and that triangle is all in one plane. So it's a triangle in a plane. That's where the name comes from. If there's three regions of electron density, so two bonds and one lone pair, then the shape of it is bent. All right. So the shape and the electron geometry are the same. All right. If no lone pairs. Okay, the shape and the electron geometry are different if there are some lone pairs. All right, next up we've got the tetrahedral family, which we just saw. We can have four regions of electron density for the tetrahedral family. So the tetrahedral family, this is our electron geometry. And then the shapes are down here, either tetrahedral, trigonal pyramidal, or bent. Those are based on how many lone pairs there are. No lone pairs, it's tetrahedral. There's one lone pair, it's trigonal pyramidal. If there's two, it's bent. All right, we also can have what we call the trigonal bipyramidal family. So here we have a triangle. That's where trigonal comes from. There's a pyramid that's formed up top, and there's a pyramid that's formed down below. That's bi or two pyramids. That's where the name of that one comes from. All right, so again, right, if there's a lone pair, it's called a seesaw shape, because if we kind of looked at this thing drawn more like this, right, it kind of looks like a seesaw if I turned it over here more on its side, like that. We've got a T-shaped, again, if it was more on its side than the way that it's drawn there, it looks like a T. And then that last one looks kind of funny, but if there's three lone pairs, then it becomes linear. And then our last one, oh my gosh, the pictures are incorrect for our octahedral family, so ignore the pictures. All right, I will try and fix that on the ones that are, I think they're right on the PowerPoints that you can look at online. So the pictures should be right there, but these ones are all goofy looking. So, but there are some different things, so just ignore that part of it. Yeah. Okay, but I like to use just like a table like this where if I'm drawing something, right, I can figure out, okay, so number one is any bond counts as one region of electron density. And any lone pair counts as one region of electron density as well. Okay, so if we had and we only care about the central atom. So we don't care about the ones that are around it. So we're only caring about this. We're talking about the shape. We look at the central atom. Okay, so sulfur in this case has 3 regions of electron density. It's got a double bond and 2 single bonds. That's 3 regions of electron density. None of them are lone pairs. So if I want the electron geometry, there are 3 regions of electron density. It's trigonoplanar. The shape, which is sometimes called the molecular geometry, but the shape of it, there are 3 regions of electron density and no lone pairs. It's also trigonoplanar. Okay. What about earlier we had that ICl5? Okay. Okay, the regions of electron density around our iodine. There's 1, 2, 3, 4, 5, 6. And one of them was a lone pair. Okay, so the electron geometry is octahedral. The shape, 6, but one of them is a lone pair. So we're going to call that square pyramidal. Okay, so you can use these tables, just to figure out what they are. Once you've drawn them, if you can draw them, then you just use the tables in order to get there. All right, so whatever it is, you can just kind of run through those. All right, you should have plenty of practice doing these as well on in-class problems and stuff along the way. All right, lastly is electronegativity. Okay, this is basically whether a bond is going to be what we call nonpolar, polar covalent, or ionic. And so you should be given an electronegativity table like this, and you can look up values along the way. All right, and so nonpolar covalent, all right, they're going to equally share electrons. All right, and so that is where the electronegativity difference is between 0 and 0.4. So what you're going to do on here is you would look, and if I had, say, well, we're going to do this on the next slide, but let's say that I had, all right, anyway, let's do the polar covalent. All right, which is a non-equal sharing, which is where we have an electronegativity difference. This is a polar bond of 0.4, all right, up to 2.0. And then ionic bonds are where we've got that complete transfer of electrons That's electronegativity difference of 2.0 and above. All right, so we can just look up those values in these tables. So again, on the next slide, right, we're going to have like a hydrogen-hydrogen bond. So the electronegativity difference is 2.1 minus 2.1, which is 0, right? Or if I had, say, a hydrogen chloride bond, right, I would look, I've got hydrogen is 2.1. We're going to do the absolute values of these, minus our chlorine, which out there is 3.0. I would have an electronegativity difference of 0.9, so I would say that this is a polar covalent bond. Okay, so again, right, so here I've got like hydrogen and hydrogen, 2.1 and 2.1, those values, right, from a table, you would have to be given these values in order to solve these things. All right, but again, if they're between 0 and 0.4, they're nonpolar covalent. 0.4 to 2.0, they're polar covalent, right? And 2.0 and above, it's an ionic bond, right? And so I'm giving the example there for my ionic bond of sodium and chloride. Sodium is 1, chlorine is 3. The difference between those two is 2.0. Right? That's a complete transfer of electrons there. It's an ionic bond. Okay, that ends another chapter. That one's probably going to be the longest chapter. Sorry about that, and we'll see you back here for chapter 8.